then let me go directly to the solution of incompressible Navier-Stokes equations, since we will have a couple of problems there. What problems can you expect? Remind what kind of problems we had for the find volume method. No wonder in find the checkerboard pressure field was one of the problems in the find volume method or find difference method. So the ambiguity that you don't have well-defined pressure. I mean, in find differences, we have seen that this might be that, like, if you do the discretization wrong, we have seen that having such a pressure distribution with absolutely arbitrary values, if you discretize the pressure gradient term, discretizing the Navier-Stokes equation at this node, you use for pressure gradient calculation these two values, then we remember that, well, the pressure gradient is 0. Well, this one is also 0, but you've got completely arbitrary values in every second node. So there is some singularity in the system. We've got the same, we've got a completely very similar problem in find elements, but the way how you solve it is different, well, because the method is different. Well, first of all, it turns out that if you want to solve the incompressible Navier-Stokes problem, then you can't work with linear find elements. You simply can't, because this will always be unstable. So if you select such triangular elements to discretize the velocity space and the pressure space, it will be wrong. It will be unstable. Like it's the analogy of having, like, the proof why it's unstable is for a longer lecture, that not for now. Yeah.
Have you tried it somehow in your previous works to use one elements to solve Navier-Stokes, and it's really unstable, or in some cases it can work, but really poorly?
To be honest, because I know it's unstable, I have never tried to do this.
Okay. I was wondering if it may work in some cases, but or something like that, or never mind.
What's the most common solution to this problem? The most common solution is that in find elements we introduce two different function spaces for representation of velocity and pressure. And people have investigated different pairs of these of these function spaces which make sense and which generate stable pairs. I would say the most common one is having the linear representation of the pressure fields. So you're using these nodes for pressure. That's fine. Pressure is linear. But you are using second order nodes and second order triangular elements for velocity. Okay, I think the other choice, but I think like very academic, and you would need to check that because I'm not sure, that you can use, for velocity, you can use linear shape functions, but then you need to have pressure which is constant across the element. And to be honest, you don't want to have simulations with pressure that is constant across the whole element. So I think this one works, but it's really not used often. This one is very, very popular. And these elements are, if you want to search for them in the literature, they are either called, well, this one will be probably like, Q2P1, meaning that you've got second order representation for velocity and first order for pressure. You've got the same counterpart for the quad element. Yeah.
Do you know any proof that is available for someone who didn't study mathematics? Why this choice is good for the checkered problem?
You need to, like, if you want to find and study the proof, and that's what I want to tell you, is the name of the condition that will tell you whether the pair of velocity function space functions and pressure functions is a stable pair. It's called the LBB condition. LBB conditions, which comes from three names, and it's Ladizhenskaya. Yeah, I think it's Olga Ladizhenskaya, a Russian mathematician or so. Babushka, Bretzi condition. And the same condition, exactly the same one, is also called the infimum supremum condition. And if you go to the derivation or to the proof, you will find like what kind of equality or inequality must be fulfilled for your, like I think the gradients of the velocity function times something. And you've got a nice relation to check if it holds or not, but I don't want to go into the derivation. LBB condition, infimum supremum condition, these are two names that you should remember. Certainly you need to remember that this one, the Q2P1 elements, often referred to as Taylor-Hood pair. Taylor-Hood pair. That's one of the most common choices for finite elements, how to represent the velocity field and pressure field to keep the whole discretization stable. Okay, what's the other problem that we had for in finite volumes or finite differences? Okay, that it's difficult to solve the resulting matrix, and we will have the same because it's still a discretization of a Navier-Stokes problem with a different method, but the property of the matrix will be the same. But I don't mean that. There is a particular problem with the discretization.
Convection stabilization. So fluid scheme.
Exactly. Stabilization techniques for highly convective flows. Again, as you remember, for the finite difference discretization, we had this condition that for advection diffusion, the Peclet number must be lower than 2. Then even with central differencing, you end up with this scheme that does not produce oscillations, that does not produce the wiggles. Now, it's the same story in finite elements. If you go with the advection velocity too high with respect to the diffusivity, and too high means not particularly high for physical quantities, also the finite elements will produce the oscillations and wiggles. What's the remedy? Does anyone know how to create upwind for the finite element discretization? You probably know. Probably yes. Okay. The idea is the following. Imagine for a while that we want to solve something like that, steady case. If we generate the weak form, well, what do? We need to multiply by the test function. We need to multiply that by the test function. That's actually it. I will not repeat the derivation of this term because we have done it a couple of times. Let me just write. It's I need to have some more space. So we don't change anything in the convective term, but how did we discretize that? Equals like, I think, plus. Right? Okay. Now, what's the trick? Do you remember how we call the method that uses the same functions as test functions and shape functions? Exactly. It's the Galerkin discretization. Right now, if we want to do something that is similar to upwind, the trick is that normally when assemble equations for this node, we would have such a test function that goes like this. Yeah? Now imagine that the flow is coming from here with some advection velocity. What you want to do is what you do in finite volumes or finite differences is you neglect everything happening downstream of your node and taking everything that is upstream of your node because it's where the information comes from. So you want to do the same in finite elements. One of the historical approaches was, okay, let's add some quadratic function to that to produce like a, something like that. To take lower weights here, higher loads here. It was one of the ideas. I don't know if still commonly used. But right now the very, very popular method is a bit different. If the original function looks like that, let's do it the other way. Let's take more of that function upstream of the node, and let's lower it by the same amount in the downstream node. Okay? You just take more of that, and you subtract the same value from the downstream node. intuition, is intuition okay? Like you're putting more weight on what is happening upstream of your node, and you much more neglect what is downstream. Now, there is a very, very easy way to write such test functions. Well, because what you do is normally you would have V functions like that. And it's very, very easy to extend and to generalize to many dimensions. Like, let's assume some modified test functions. How do we modify them? We modify them the following way. Let's take the original functions, and we need to plus some coefficient tau A times gradient of V. Now, let's have a look at that. Let's neglect the coefficient. It doesn't matter so much right now. What it means, like, if you calculate the gradient of the original test function, for such a test function where it's 1 and minus 1, and this scalar product with the advection velocity vector field, like it really selects, I've got positive sign, so on the upstream side, I add value. On the downstream side, I subtract. Okay? This parameter is used to like balance how much of upwind I want to use. And do I really want to go very, very high with the upwind, or maybe I just want to add a small fraction to that and subtract a small fraction. Obviously, upwind for finite elements has got the same properties as it had for finite differences or finite volumes. I mean, it adds diffusion. So if you can, you rather want to keep this parameter small, but you want to keep it, but you want to keep such a value of this parameter to keep your scheme stable. Questions? Okay.
What about the property? Like, okay, I can imagine that at the central point, the point that we define the test function at, we can just assume that it's 1 still because it will be in the middle of these two lines. But what about the test function being 0 everywhere, like at the points?
You mean here?
Yeah.
Well, nothing changes. Like you see,
Yeah, but at the boundary point, like it's some positive value or negative value at
here
in neighbor point.
does not produce any problems.
Okay.
Okay, and now I want to introduce the name of this technique. The name of this technique, first of all, you said that if you're using the same shape functions and test functions, such discretization is called Galerkin discretization. Now, the class of discretizations in finite elements that use different functions as shape functions and test functions, they all are called class of Petrov-Galerkin discretizations. Now, that particular one is called streamline upwind Petrov-Galerkin, like, because it goes like with the streamlines, because it's aligned with the advection vector field, where upwind, because it certainly does upwind, where Petrov-Galerkin, so the abbreviation is SUPG, and it's how it's called. It's the SUPG discretization. There are also other techniques to stabilize the problem. One of them, I cannot go into the details right now. One of them is GLS. GLS stands for Galerkin least squares. You can reformulate this problem with the instabilities. You can reformulate to like generating, like minimizing the square error, like to minimize the oscillations, and you can reformulate the problem. Then you come up with the formulation of the Galerkin least squares. Probably two most popular techniques to stabilize advection, like highly convective problems in finite elements. Questions to how you build the test functions? What happens if you want to implement that? Now, you see, if you want to implement that, what do you need to do? So you need to replace this V by V plus coefficient A times gradient of V. So you see that you generate more terms. Like the first one is the original one. But additionally, you've got something which is the advection velocity times the gradient of U times, well, some coefficient times velocity times gradient of V that clearly already, especially for higher order elements, it's not a constant value, so it adds the degree of the function that needs to be integrated. So one difficulty is that you probably need to use a better Gaussian quadrature with higher number of quadrature points. But my first question still is, can you replace just one of them? Just I have written here what happens with this and that.
SUPG, they are not replaced. You should only replace in convection parameters.
Like on the left hand side, the gradient stays the same, so does it? Like it's the gradient, so it doesn't change when you add.
Oh, or rather, it can be implemented that way, but in the perfect world, it should be applied to every.
Mm-hmm.
It will work in case if we apply in.
Just imagine. Let's start from scratch and from the strong form of the differential equation. What you are allowed to do when deriving the weak form is, no one said that deriving the weak form is even not discretization, but no one said that during derivation of the weak form you need to assume anything about what is U and V. So you can use them from two different function spaces, and that's what the Petrov-Galerkin assumes. But you need to start with the strong form and multiply it by some V. And you need to multiply the whole equation by V and then integrate. So if you can choose such V functions, no problem, but you need to apply it consistently to each term in the equation. Then you do the integration. And I said you need to consistently apply it to each term, and then such a method, if you reapply it consistently to each term, is called consistent SUPG. Now, you had pretty good guess. Like if you work with linear finite elements, then okay, here you've got the gradient of V. So if you and your V is already linear in your linear finite elements, then if you calculate that, if you calculate here gradient, it's a constant value. So if you want to introduce something more, you'd have constant value here. Well, differentiated, it's nothing. So for linear elements, that's true. It simply vanishes. But if you work with second-order elements, it does not vanish. But that's true that people both use consistent SUPG, meaning that you use these test functions for all the terms and the integrals. But people also use inconsistent SUPG because it's not mathematically okay, but it turns out that it really stabilizes the scheme. You've got the problem with the convective term, and if you only replace the V function in the convective term, it works. It stabilizes. So both things are used. Sorry?
Not great, not terrible.
Good. The last topic is let's try to write the Navier-Stokes equation. We already know that we need to use different function spaces for velocity and pressure discretization, and we know how to handle the instability with highly convection-dominated flows. Now, let's take the Navier-Stokes equation. Okay, that's the strong form. What do we need to do next? Yeah. V times V, or let me rewrite and integrate. That one is something that we already know. What would it produce? We know it would produce minus ni, right? Plus okay. Now, with that one, we really don't do anything. We don't change it. But if you want to do the discretization and you want, the Navier-Stokes equation is clearly a nonlinear equation. we typically solve nonlinear equations by solving the whole series of linear subproblems. So when assembling the matrix for solving the Navier-Stokes equation, you usually need to assume the convection velocity. Basically take it usually from the previous step of the iterative process, or you might have other guesses. I will talk about that at the end of my lecture. So you assume that you know this velocity, and then you've got the linear problem. If that one is known, then you've got the linear problem. So you discretize for the unknown coefficients of the U field. Here, what does it generate? The domain of integration is constant in time, so we can take the derivative out of the integration. We've got d dt plus, here nothing changes. What will this produce? Exactly. Because, well, U is given by some j, uj times, well, phi j. And this one is phi I. So this one will generate like phi j, phi I needs to be integrated, then uj. I've got a problem with the vector notation now. Because that's tricky. Like, I mean, it's easier to explain how to implement that, but to keep it formally okay is not obvious. Okay, let me not cover that. I want to discuss with you in a minute how to re-implement vector problems in finite elements. But let's not stick to the vector notation, which is not neat. But you still, what you do in finite elements is you want to transform this term. Why? You want to transform this term because, remember, we are using the linear interpolation for pressure. So this means that calculating the gradient of pressure would leave us with the constant gradient across the whole element. But since we've got with second order shape functions for velocity, we also work with second order test functions for velocity. So calculating the gradient of this term would give us a linear function. So what we are doing with that term is the following thing. Like can be transferred as minus times okay. And let's see, it's easy. Well, it's easy. It's fine to calculate the divergence of the second order test function because it still gives us a linear term times linear pressure is a much better way of calculating that than the original form. This one can be translated to what do we need? Right? The Gaussian theorem. So finally, what we have plus some approximation, gradient of u times v. Let me assemble that. We need to take this. Well, sorry, one more thing. Diffusion matrix certainly goes on the left-hand side, which means that we need to take this plus ni. What's left? The other thing that is left is this term. If we put it on the left-hand side, because pressures are unknown, then it goes with the plus sign, and then it's minus. Well, check me. This goes on the left-hand side. I want to take this on the right-hand side. So this would be N P times V. 1 divided by rho, 1 divided by rho. And we have already taken this term, and let's take this one. This one is the only that we've got left. Is it okay? Okay, if it's fine, then let's have a short discussion. Test functions, we can calculate them. This one will be transformed to the sum of the shape functions times the unknown coefficients. We do some approximation of the convective velocity. Here we will have the gradient of u, but u will be replaced by shape functions times unknown coefficients. Gradient of shape functions can be computed. We did it for the diffusion problem. Right now it will be easier. Well, it will be easier because we just have one gradient. We don't need to multiply it by the different gradient, but we need to apply the geometrical transformation here. We have already derived that. And like here, the divergence of the second order test functions can be computed. So we can integrate that. This one will be replaced by pressure values, the nodal values, times the linear shape functions of the linear shape functions for the pressure. And this one will implement the outflow boundary condition. I will go into that in a minute. Some question?
I guess it's always implicit?
It's always implicit. Actually, in finite elements, it's always implicit. Why? Because for finite differences, we were able to produce an explicit scheme to calculate the new value. Why you can't infinite elements. You can't, because even if you write a very simple triangular linear element, what's your mass matrix? Your mass matrix is like integral of phi 1, phi 2, etc. Phi 1, phi 1, integral of phi 1, phi 2, etc., which I mean that you will have a third term, and the local mass matrix is 3 by 3, and it couples all the three nodal values with each other. So you cannot write it explicitly, because even on the local level, you need to solve a system of linear equations with such a matrix to calculate the nodal values. So if you assemble the global problem, you have no way. You have no way to decouple the nodal values at the new time level from each other. So it's always implicit. But people in finite elements, they do something that sometimes helps with the stability, or sometimes helps with the computational cost of solving the problem. And they attempt doing what you asked about. Like something that is done is matrix lumping. And matrix lumping means that you take all the values from the respective row, you add them together, and you put them on the main diagonal. It's the approximation. It's not literally correct, but it generates a diagonal matrix, which means that you can write an explicit formula for something. I think matrix lumping is used, for example, if you want to generate some preconditioners. Then you want to have an approximate solution. You do matrix lumping. You come up with explicit formulas for something that come from finite element discretization. Any more questions so far? Okay. If you want to solve such a incompressible flow problem, what kind of boundary conditions would you want to impose?
So the zero velocity, no slip, but the cylinder has bottom and top wall.
Exactly. And here you probably want to have some prescribed velocity profile. Okay, so Dirichlet boundary conditions.
Pressure at the outlet.
And pressure at the outlet. For example, 0.
Is it compressible or?
Incompressible. Okay, so with the Dirichlet boundary conditions for velocity, it's nothing new. Like we need to do in the implementation what we've been discussing for the scalar problem. For this open boundary condition, it's not something that is evident, but if you do the derivation, or if you find in the literature the expression, proper expression that you can derive from the Navier-Stokes equation, if you write the Navier-Stokes equation at the boundary, then what you come up with is and allow me to skip equals to something, for example. And it's not, sorry, it's not something that is evident that it implements the open boundary condition, and it's not something that is evident that can be easily derived from the Navier-Stokes equation. It would take us probably like half an hour or so. So I don't want to repeat that. But the nice thing is that if you have a look at that, and it really comes from Navier-Stokes equation, if you have a look at that, it's exactly what we have sorry, I might have done some error in the signs. Can it be? I think it must be. Because what should be visible is that we've got P unit normal vector here, and we've got this Ni unit normal vector and velocity gradient here. So we can replace these two terms. We can replace these two terms. Sorry for.
Yeah, there should be a minus on the right-hand side and
here.
Plus, yeah, and plus on the left-hand side, I believe.
Okay.
Am I correct?
No, the left part was okay because.
Are you sure? Because you've got like one minus there, then there is minus there. So.
Okay, yeah.
So it's okay. Okay. Well, depending on the convention, it should be like that. So it's really the same. I mean, depending on the convention, because in many incompressible codes, you will start with a Navier-Stokes equation that looks like that, without division by density. And it's very, very common that codes are implemented like that. And you simply assume that your pressure is the real physical pressure already divided by density. That's why I have initially written it like that. And if you want to compare, obviously, this one does not coincide with that because we've started with two different conventions. So if we use the physical way, then it needs to be implemented like that, and everything is fine. What is that function? This function is and it can be. You can write proof for that this is the average pressure at the boundary. So locally, you might have different pressures, but the average value of the pressure imposed by this boundary condition will be equal to this function. So if you want to have zero average pressure at outlet, that means, and you replace this by what? What do you need to implement? Nothing. You don't need to implement nothing. You don't need to implement anything to apply the outflow boundary condition for the Navier-Stokes problem.